So welcome back to the analysis seminar. Our speaker today is Gennady Uraltsev from the University of Virginia, and his title today is Banach space-valued harmonic analysis. Gennady?
Okay. Hello. Thank you for having me, for the invitation, and I'm actually quite excited to give this talk at the ICMAT or in Madrid, where Spain is actually known for lots of the results, the things that I had to learn to actually get kind of inside this area of Banach space-valued harmonic, and it comes from people people in Spain. So yeah, so actually I'm also excited to hear what you guys think about what I'm going to be talking about. Okay, so at the beginning I will just give an overview and my understanding of why Banach space-valued harmonic analysis can be important, interesting, or anything like that, and then actually get to the specific kind of results that I managed to work on. So okay, so at the beginning, let's see. Oh, sorry, this the screen is a little bit covered here. Okay. So what are we in harmonic analysis? One can say that deals with linear singular integral operators. So what does that mean? So generally, one can say that practically any linear operator on function spaces, if it has, for example, some invariance with respect to translation, all of these hypotheses can be relaxed, but for the sake of example, can be given by a convolution kernel. Okay, so you take so the input is a function f, the output is given just by a convolution. What do we mean by a kernel? Well, a kernel is just, well, something that could be locally integrable for a function, but it also can be a distribution if you want to generalize. And actually, it can be shown that any continuous operator from a very good space Schwartz functions into distributions, tempered distributions, that is translation invariant is necessarily given by a convolution kernel. So okay, so this provides some structure of what we're going to what we want to study is let's say linear operators between function spaces, and let's see what are the at least the most trivial results that we can state about this this kind of linear operator. Of course, the boundedness, any property of our linear operator is the whole point is try to express any of these properties in terms of properties of the kernel. So for example, if the kernel is actually an L1 function, then just Young's convolution inequality, so this is a standard result from real analysis, tells you that K convolved with F, so G of F in any LP space is bounded just by F in LP times the L1 norm of K, because essentially this becomes an averaging operator. The convolution with an integrable function is you just take F and you smudge it a little bit. So by convexity, essentially a triangle inequality, you have this bound. Okay, but unfortunately, or fortunately for us, because that guarantees us a job in a certain sense, not all convolution kernels of interest are actually locally integrable. And I guess the most famous integral operator given by a kernel that arises more or less everywhere, complex analysis, PDE, is the Hilbert transform. Okay, so what you do is you convolve the function f with the kernel 1 over y. Now and this is in one dimension, so we are on R1. So 1 over y is a kernel that barely fails to be integrable, because if the explosion around 0 was anything slower than 1 over y, you would have integrability. Converse, if you had decay that is a little bit quicker at infinity, you would have integrability. So this represents kind of the limit point. And also and it is known, and there are multiple proofs available, that the Hilbert transform actually does map LP functions into LP functions, with a slight difference with respect to the non-singular result that this holds true for P between 1 and infinity, excluding the endpoints. So what's called in the reflexive range. Okay, so generally one considers the Hilbert transform as a prototypical Cauldron-Sigmund kernel, and Cauldron-Sigmund theory, well, just describes a class of barely non-integrable kernels that actually give rise to bounded operators, okay? So what is a Cauldron-Sigmund kernel? Well, it is a kernel that kind of looks like the Hilbert transform. So what does that mean? So first of all, we have outside of the singularity, so outside the origin and outside of infinity, the kernel corresponds with a usual function. And in particular, you have, well, one can relax a little bit these conditions, but what one has is just some bounds, pointwise bounds on the value of the kernel and on its derivatives. Now, if you wish, the Hilbert kernel 1 over y satisfies this inequality directly. So alpha is a multi-index, so that's just taking some derivatives in some directions. If you take alpha to be 0, then you just have that k of x is smaller than x to minus the dimension. That is exactly what here it would be 1 over y. So that's exactly the Hilbert kernel. By homogeneity, you check that similar conditions hold for the derivatives. Another condition that is you have to input into the Cauldron-Sigmund theory is that you have some kind of, like a priori, you know some kind of boundedness. So for example, that you know that your operator is bounded on L2. Usually checking boundedness on L2 can be done somewhat simpler than checking boundedness on any other LP because of Hilbert's orthogonality, Hilbert-based techniques. But though there are things like T of 1 theorems and whatnot that actually allow you to forego this kind of assumption and give some kind of other testing conditions on the operator. Anyway, so what Cauldron-Sigmund theory tells you that if you have these two assumptions, then you actually have bounds for all p between 1 and infinity. So at least for the sake of what we're thinking, like what we'll be using here, we think of Cauldron-Sigmund theory as a way to extend boundedness for one exponent to extrapolate it to a whole range of exponents. And actually, one of the interesting things of Cauldron-Sigmund theory is that it actually never distinguishes between any p's in the reflexive range. So if any kind of object falls into the domain of Cauldron-Sigmund theory, the bounds are going to be available for all p in the reflexive range. Okay. So here is the comment. What's the classical way of, for example, showing that the convolution operator is bound in all two? Well, an orthogonality-based technique is the Fourier transform. You just take the convolution, you take its Fourier transform. The Fourier transform is an isometry on L2, so that gives you the first identity. Then the second identity is just an algebraic fact about that convolutions get sent to products by the Fourier transform. And then, well, you have k hat f hat, the product, and in L2, well, clearly this is bounded by just the L infinity norm of k hat times the L2 norm of f hat. And this inequality can be saturated as long as you just create an f hat that sits where k hat is large. So this is actually a very sharp result. And then what you do, so this this should be an infinity, that's a typo. So and then you just use Plancherel's identity or isometry of the Fourier transform, and you get back the L2 norm of f. So this is so essentially, if you show that k hat is a bounded function, you're already good with showing L2 boundedness. Well, as I said, there are other ways of showing like things that don't actually involve computing the Fourier transform, but these are kind of beyond what we're doing right now. But for the case of the Hilbert transform, one way of showing that this falls precisely into this theme of Cauldron-Sigmund theory is just computing the Fourier transform of the Hilbert transform of a function that is pi I sine, a bounded function. This can be computed using just appropriate basic techniques of complex analysis, and here we go. Okay, so this it's an overview of what Cauldron-Sigmund theory is. So let's give an interesting application for PDEs that will motivate also I guess what does it mean to do Banach space valued harmonic analysis. And an important question, for example, when you're defining summative spaces is whether if you control the Laplacian of a function in LP, supposedly here I said on R2, but this holds on any space. Is it true that you control the mixed derivatives in LP? So somehow does Laplacian control all the derivatives? And the answer is yes. And well, let's see why this falls into the realm of Cauldron-Sigmund theory. Well, we compute the Fourier transform of the second derivative here on the left-hand side. So by just standard identities, taking derivatives corresponds to multiplying on the frequency side. What we want is we want to make the Laplacian appear. So what we do is we just divide and multiply by the thing that looks like the Fourier transform of the Laplacian. And here we get the expression, what we call the symbol. So you see, we have computed the Fourier transform of the quantity on the left-hand side, and it is just the right-hand side times a function of like a specific function of the variables. That's called the symbol. So this is we know to understand this as the Fourier transform of a kernel. The kernel can be computed. This is a composition of what's called Riesz kernels that generalize Hilbert transforms to higher dimensions. So kind of what we get is, well, we can check that either that this kernel, so the anti-Fourier transform of this object, is in effect a Cauldron-Sigmund kernel, or otherwise there's a mirror theory of Cauldron-Sigmund that exists at the side of multipliers that tells you, well, what are the corresponding properties or inequalities that you would need on the Fourier transform of a kernel to make sure that it's Cauldron-Sigmund, and they're actually quite simple. So essentially, there are zero homogeneous relations. Okay, so this is, and well, since this is just the Cauldron-Sigmund kernel applied to the Laplacian, there we go. We have the results, so the LP the bounds that we require, so they are true. Okay, so now the question becomes, what happened? Like, what's the corresponding question for Banach spaces? So what do we actually mean by Banach spaces? Well, first of all, we fix a Banach space, capital X, and now instead of having functions that are LP valued, I guess, in complex numbers on or defined on R2 in complex numbers, now they're valued in some functions, like some space. And we can ask exactly the same question. Now, possible question would be, why is this interesting? Why is this useful? This arises in multiple cases, but for example, you could imagine that if you're studying some kind of evolution equation, so an evolution, a PDE that is an evolution equation, so you have an evolution in time, and at every fixed time, the fixed time slice is a function of space. So you can kind of forget about the fact that you're a specific function in space, and you can just say, well, you know, for every time my function is valued in some kind of Sobolev space and something of the spatial variable, and just call that a Banach space and try to forget about, like, you know, the specifics of that. And then you know, when you're doing some kind of Duhamel formula, to like when you're solving an evolution equation, you naturally get singular integral operator. So these kind of questions arise, maybe not exactly in the form that I asked here. So now let's try to run the whole technology again for a Banach space. So we can define the Fourier transform in the same way that it's usually defined for functions valued in a Banach space. We do the same computation, we obtain exactly the same symbol, so we obtain exactly the same kernel expression, you know, the 2D convolution. Now, what's the problem? The differential inequalities on the kernel are very nice and they are satisfied. The symbol, we know that it's a bounded symbol. However, we have a big problem that even though the symbol is bounded, we can't really prove the L2 bound. And why is that the case? So where does the problem arise? The fact that for Banach valued functions, even though you can define the Fourier transform, the L2 isometry does not hold, because that is something that is typical, like, of orthogonality techniques. And if X were a Hilbert space, then you could actually make it work. But if X is not a Hilbert space, this equality is generally, even the inequality is generally false. So the problem is that you could try to apply the techniques of Cauldron-Sigmund theory to bootstrap all exponents p, but you don't know with which exponent to start. You know, you don't have an L2 theory. And actually, if your Banach space is not a Hilbert space, 2 is not nicer than any other exponent. So now this was kind of like how do you even get anywhere? And the fundamental intuition of how to do Cauldron-Sigmund theory for Banach space valued functions was given by Buchholder and Bourgain in the 80s. That actually gave a very good characterization of when some form of Cauldron-Sigmund theory works. Now, what they showed is the boundedness of the Hilbert transform, and what they showed that the Hilbert transform is bounded for on LP if and only if X is UMD. UMD means unconditional martingale difference. I'll explain what that actually that's one of the few things that I'll define in depth just shortly. Okay, so now the question for which P, the interesting thing is it doesn't really matter, because as a matter of fact, once you have it for one P, you just have the Cauldron-Sigmund machinery that allows you to extend it for any P. And also that, once they gave this fundamental input, then, the theory progressed, and one showed that you can do everything that usually you can do with Cauldron-Sigmund theory. You just have to work a little bit, put in elbow grease, and then you get little with Paley theory, you get Michelin-Hormolder multiplier. So everything you expect from Cauldron-Sigmund theory works if X is UMD. So now let us actually see what UMD is. Okay, so actually, as the name says, unconditional martingale difference. So there's martingale. So this is a probabilistic concept. So let's actually see what martingale are we talking about. So we start with a very standard construction, and that is the filtration of dyadic intervals on a unit interval. So what you do is you take the unit interval, 0, 1, let's say, and what you start doing is you start subdividing it into halves. So you take the interval 0, 1 half, 1 half, 1. Actually, sorry, a question. Do you see the pointer?
Yes, we do.
Talk?
Yes,
okay, good.
Yes, we do.
So you have the two halves, then you have them again, and so for every order you have, for every order n, you have 2 to the n intervals of a length 2 to the minus n that are kind of nested in this painfully familiar dyadic tree structure. Okay. So now. So what do we do? For at each level n, we actually can consider the generated sigma algebra by these sets that is actually quite trivial because the sets are few, they're finite, so it's just finite unions of the basic sets. We can define the conditional expectation, or what En was called, though, so that projects f, any function, any measurable, let's say locally integrable function from 0, 1, into a Banach space. So you can also think of it a complex valued, but also Banach space valued, into functions that are constant on each interval of Dn. Okay, so that actually means that's you can actually see that that's in the case of in which X is a Hilbert space, that is an orthogonal projection onto the subspace of L2 measurable. L2 functions measurable with respect to the sigma algebra generated by the n. So the expression is, you just substitute the whatever function you have by its averages over each interval. Okay, quite an easy fact to prove is that, and this just follows by appropriate density arguments, that if f is an LP with, so here I omitted the quantifier of p, so it's in the reflexive range between 1 and infinity, then the limit of these conditional expectations, so as you refine and refine, for example, in LP norm is your original function. So if you take smaller and smaller averages, you converge to your original function. And for example, it's clear for continuous functions, and then you can just use the density argument. So now so here, remember UMD is unconditional martingale difference. So now we need to introduce a difference. So how do we introduce difference? We just telescope. this expression. And so we say we define delta En of F to be just the difference between one step and the next. We telescope the limit fact and just write it as a series. Now at this point, the adverb unconditionally becomes clear where to put it, is that this sum that is an infinite sum, you ask that it converges unconditionally for F in LP. So what does it mean unconditionally? That means that you can rearrange the order of summation and you still have LP conversion in whatever order you rearrange, as long as you eventually get all of them. Now, once again, UMD is, one should actually formally define it as PUMD, so a different space for every possible exponent P, and then prove that all of these notions of UMD are the same as long as P is in the reflexive range, okay? And this is, once again, has a very much of a flavor of Cauldron-Sigmund theory. Actually, to be fair, currently, this has been kind of well established, and at least unless you're worried about more subtle and specific details, usually the way to prove a result in Cauldron-Sigmund theory is first prove it for this model with martingales, and then there's just a kind of a philosophical way in which you just write exactly the same statements and you transfer them into the continuous setting for no longer for these martingales, but for actually Cauldron-Sigmund kernels. So this kind of insight of Bourgain has become not only a theorem but also like a method of thinking about what Cauldron-Sigmund operators really are. Okay. So you see, somehow it seems that you have this if and only if before. So this characterization is if and only if. So it seems that there's nothing actually interesting with Cauldron-Sigmund theory on valued in Banach spaces, because it seems this is all you need to ask. However, actually a much richer theory occurs if you consider what are called multilinear Cauldron-Sigmund operators. So let's see where does the idea of multilinear Cauldron-Sigmund operators comes from. So we saw that one important application of Cauldron-Sigmund theory was controlling cross derivatives with a Laplacian. So let's actually also write down some kind of now not linear but a bilinear identity that involves derivatives. So the simplest one that you can come up with is just the Wideness Rule. You have two functions on R, you take their derivatives, the derivative falls either on the first function or on the second function. So you can ask, when do you have some kind of LP bounds of the derivative of the product in terms of LP norms of the derivatives of the functions and the LP norms of the function itself. And as a matter of fact, just applying Holder's inequality, basic real analysis, gives you this identity. Now, this doesn't seem to involve any kind of advanced technology, but now let's actually rewrite this in a slightly different way. So right now we're doing scalar valued, by the way, there's no Banach space occurring quite yet. So let's write down the derivative of f and g as being, so we just rewrote everything. And now what we do is, instead of writing an entire derivative, we make the derivative fractional. So we raise the derivative to a fractional non-integer power. Now, what is actually a fraction of a derivative? Well, there are multiple ways to define it. You can define it spectrally or for the Fourier transform, you just say, well, taking a derivative is multiplying by psi, I psi, whatever. Remove the constants, put an absolute value, and instead of multiplying by psi, multiply by psi to a certain power, positive non-integer power. Okay, so this question is now, well, it also has an answer. So this is a statement, a fractional Leibniz rule. So it behaves exactly like you expect, with a certain exception that actually, interestingly enough, now, when you're proving this thing, you actually allow the value plus infinity. So somehow the range expands a little bit. So while standard Cauldron-Sigmund theory was only in the reflexive range, and generally properties of these spectral operators work in the reflexive range, here you are actually allowed to have the functions be infinity as long as not both of them are infinity simultaneously. Okay, so now let's actually see what it has to do with Cauldron-Sigmund theory, and here this one involves a little bit of spectral computations. So let's just at the beginning express the product of two functions using the Fourier inversion formula. So we write the first function and the second function, the Fourier inversion formula for both, and we take their product. Now, using Fubini, we rearrange the integrals, use the properties of exponentials, and we have this expression, the Fourier transform of the first function, the Fourier transform of the second one evaluated in two different variables, and then you integrate in 2 to the pi I xi1 plus xi2, so in the sum of the frequencies. Now, this actually has a very nice graphical interpretation. You take a plane with the two frequencies, you take the formal tensor product of the two Fourier transforms, and then you actually notice that this integral is you're integrating over all possible sums, and then you're integrating this tensor product over all possible xi1 and xi2 that add up to a fixed xi. Okay, so actually here. So here there's a one-dimensional Lebesgue measure missing from this inner integral. So at this point, you can see this as a Fourier inversion formula of something, that is this expression in parentheses here, and now you know how to apply a fractional derivative. So this is what you get. You apply the fractional derivative by multiplying, okay, this should have an S here. So you're going to set that, I forgot to write S, you could set it to be equal to 1. So now what do? Well, you have to work with this expression, and you have to make the derivative fall either on the function f or on the function g. Now this is like in the case of the actual derivative, this is easier because of just polynomial identities. In the case of the absolute, like the fractional derivative, this is not trivial. So what you do is you look at this thing, at this plane, and you separate it using some smooth partition of unity into two portions that are associated to cones. So either when one frequency xi2 is larger than xi1, or the opposite when xi1 is larger than xi2. How do you do it? You choose some kind of smooth cutoff function on the real line, and then you just evaluate in the quotient of the two of the norms of the two frequencies. So then what you can do is you transform your expression, you make this xi1, xi2 appear again, then you introduce this partition of unity, so you have this partition of unity function in xi1 over xi2, plus the other one that we're not going to be concerned with right now because it's dealt with symmetrically. Now you have this expression here. Now, what you notice is that, well, in this regime, xi2 is larger than xi1. So what we do is we just emphasize this by dividing and multiplying by xi1, because you see, when we divide by xi1, we're dividing by something that is singular along the xi1. Whoops, I flipped it around. It should be xi2 here. So this should be not like this. It should be mod xi2. Something that is singular around the xi1 equals xi2 equals 0 axis. So if we do it this way, though, since we're on this cone, we actually don't see that in a singularity that we introduce here. And if you look at this multiplier that you just obtained, it actually corresponds with a Michelin multiplier. So the ones that arise in Cauldron-Sigmund kernels. Then what do you have? You have f, the Fourier transform of f, and the derivative, the Fourier transform of a fractional derivative of g. So here there should be all s's. Okay. So, and at this point, this motivates a definition. So what is a Huffman-Meyer multiplier operator, also like specific forms of these are known as paraproducts, is an bilinear expression that looks like this. You take two Fourier transform of two functions, you put a Michelin multiplier that is usually used for linear theory, and then you integrate the sum of the frequencies. And this has a corresponding characterization in terms of kernels, and well, Huffman and Meyer studied this at length, and in particular obtained the result claimed above for fractional Wideness rules. Now, of course, what you can do is you can just exactly ask the same question for Banach spaces with a little caveat, though, because now for a bilinear, you can't really multiply. So if S and G are valued in two Banach spaces, you cannot really multiply the two vectors in a vector space. So you also need some kind of operation of multiplication. So what you do is implicitly here, you introduce some kind of operator that takes each two vectors, one from the first Banach space, the second one from the second Banach space, and spits out maybe a third vector in a third Banach space. Reasonably, this operator has to be bounded, otherwise you can't really expect to get any kind of result. The multiplier here, you can think of it as scalar, so this is just a number, and here you have an implicit bilinear map from x1, x2 into x3. Though you can also think of the multiplier itself as being operator valued. That gives rise to a more difficult theory. So in the sense that the specific bilinear map can change based on the frequency, but that is, I guess that's a little bit beyond of what I wanted to talk about. So then let's see how this plays with the whole idea of UMD, of the UMD setting. Well, actually, a very recent result showed consistently that for bilinear operators, UMD is actually a sufficient condition. So while this has been kind of hypothesized, the formal, like the complete proof of this has been given in this paper, I believe. And well, that also elaborates and actually further develops the theory for operators of higher multilinearity, so not bilinear, but trilinear and so on. But that actually becomes there the answers become more complicated, and I don't want to go into that. Though one thing that you can see is that UMD is not a necessary condition anymore, because you can even see right here that even in the scalar case, you have the opportunity of having one of the two exponents be L infinity. Now, I didn't mention examples of UMD spaces, but what you should think about as UMD spaces is, for example, all LP spaces with P in their reflexive range, so except 1 and infinity, are UMD, while the endpoints are not. Okay, so here, just the fact that you have a theory that allows a singular integral theory that allows you one of the functions to be L infinity tells you that you will be able to prove at least some kind of bounds for Banach spaces that are not UMD. For example, for example, for the space L infinity. Okay. So now, and here we're starting to get closer to actually the result that I wanted to talk about, is that, and this is due to the fact that the idea of a multilinear setting actually offers you a much richer variety of singular integral operators. Okay, so here we generalize the ones that derive from a Wideness rule, but there are others. So okay, so let's see which ones we already know. So we know the pointwise product, that's easy, and that's just Holder. You don't need any kind of theory except for measure theory there. You have power products, that is the generalization of a Cauldron Sigmund to bilinear. But and then and here, as we mentioned, the form of the multiplier has this kind of the singularity is essentially in the origin, and it has this homogeneity with respect to radial rescalings. Well, what you could do is you could just also take the product and apply Cauldron Sigmund theory to each of the components separately. So, for example, take Cauldron Sigmund kernel, whose Fourier transform is just a characteristic function of the positive numbers. So what happens is that if you apply it to the function, to the first function, you get in the plane, you get a characteristic function of 0, like of the right half plane. If you apply it to the second function, you get the upper half plane. If you apply it to the product, you get the characteristic function of the portion of this plane on the upper above the anti-diagonal. Okay, once again, because how does K act? By like on Fourier side, by multiplying by this multiplier, well, the frequency of the product, that is the sum. Well, at this point, you see you have 3 of these lines. Well, this line, the one that I didn't draw, and the anti-diagonal. You could ask what happens if you pit place any other line, like, any other line passing through the origin. But the interesting setting is as soon as you're not in one of those three distinguished positions, the operator becomes actually much more complicated. So, and in particular, if you place it on on the main diagonal, what you get is the bilinear Hilbert transform. That is the prototypical example of a timescale frequency operator. Okay, so in terms of frequencies, you can express it, well, just by looking at this picture and writing that down. You can do anti-transform it in space. It has a kernel representation that has this twisted, this kind of entangled form. So you're taking a Hilbert transform, but you're applying it to two functions f and g. However, one you take it with the argument x minus t, and the other one with x plus t. Of course, if the signs were the same, it would be just the Hilbert transform of the product. So the difference of these two signs is actually the thing that makes it crucially different. Now, what is the fundamental difference intrinsically of this operator versus more standard Cauldron Sigmund, even bilinear ones, is that you have an additional symmetry. So Cauldron Sigmund operators, as we introduced them, they are translation invariant because they're convolution operators essentially, and they are scaling invariant because of this homogeneity of the kernel. 1 over t can be, it's -1 homogeneous. However, here you have an additional symmetry, and that is an invariance in frequency and translation along this red line. That is called modulation. So in particular, what it means is that if you multiply the function f and the function g by phases, the result is not going to change. Is that okay? Actually, once again, here I made a computation. So here it should be f, this should be plus, and then here this is going to be modulation by 2 eta of the BHT. So the result is not that it doesn't change, but it also gets modulated. So the modulation passes through the bilinear Hilbert transform. Okay. So this is another prototypical operator. Boundedness, so in the same way that we asked this has been studied at length starting from the 90s. The boundedness of this operator on Banach spaces has been unknown essentially until it has been generally unknown until 2 years ago, 2019, except for a result by Lacey and Hutinen several years before that proved the boundedness for a discrete model for the bilinear Hilbert transform. Okay, so, but before going into that direction, I wanted to address a very specific case of Banach space valued integrals, and these are Banach space valued singular integral operators. The thing is, you can always construct Banach space valued operators by tensoring objects that you already know. So what do I mean by this? Well, the simplest one is, for example, suppose that, pi is a paraproduct, so this expression that we saw below, so things that fall into standard bilinear Cauldron Sigmund theory. So what you can do is you can say, well, now I take my functions f, I take them not only to be dependent on on one variable x, but I add another variable. And what I do is I make the paraproduct, so this pi, act on the first variable without touching the second variable. So at that point, for every fixed point, for every fixed y, what I get is I get the paraproduct is acting in the x direction, fiber-wise, essentially. So now what one can ask is, well, first of all, this you can see this as just being a paraproduct tensor the identity, or just a pointwise product, because in the y direction, on the other hand, it acts as a pointwise product. So that's the bilinear kind of pairing between spaces. So the thing is, you can use any of these operators that we have so far introduced and tensor them by writing down formally these expressions and ask what kind of bounds you have. Now, trivially, if you actually look at, let's see, at pi tensors the identity, you can just use, so you can just fiber-wise apply the bounds on pi, so on the paraproduct, and then you can just use Holder's inequality in the second variable to obtain LP bounds on the product space. So you can, for example, if here you had paraproduct tensor identity, this inequality would be completely trivial. It would be just the application of the standard scalar valued bilinear Cauldron-Sigmund theory plus Holder's inequality. Now, however, when you are introducing, you're tensoring with something that is not the identity, the problem becomes immediately more complicated. Now, in the paper in 04, it was essentially one of the first times when these kind of questions were addressed by Muscalo, Pfeiffer, Tau, and Thiele. So, and they managed to prove diagonal bounds. So what do we mean by diagonal bounds? We mean that the integrability exponents LP is the same in both variables. However, a more Banach space perspective would be to ask, well, you interpret f and g as not being LP functions of R2, but LP functions in X, let's say, valued in some LQ function in the Y variable. So this is what's called the mixed norms. And mixed norms were actually not available for a very long time. And the question about mixed norms for all of these kind of operators that are Cauldron-Sigmund or time frequency has been essentially solved in a sequence of paper by Muscalo and Benea. So starting from 2015, improvements in 16, 18, 19, and so on. So they get full bounds that, that you would expect for tensors of paraproducts. If you tensor with BHT, there are some reasonable restrictions. There is a remark based in, once again in 04 that is actually going to be relevant for us, that BHT, tensor BHT does not admit any bounds. Okay, so this kind of, in this, what's called the multi-parameter mixed norm setting, the question is essentially settled. Why is it called, by the way, multi-parameter? Because here you do have two sets of symmetry, like an additional symmetry, or if you wish, one of the symmetries has two parameters. So the scaling symmetry now has a parameter in the first variable. So you have an independent scaling parameter in the second variable. So the two homogeneous are completely independent one of the other. However, this method does not really generalize in any way beyond the multi-parameter setting. So for more abstract Banach spaces like let's say if you don't have LQ spaces in the second variable. So let's actually compare the two methods. So what the helicoidal method of Benea and Muscalo gives, well, here I've just copy pasted a piece of the result. It's somewhat technical to understand, versus the result that me and Alex and in parallel Francesco Di Plinio and a bunch of other people have obtained. So, for example, suppose that you have the bilinear Hilbert transform, you dualize it to obtain the bilinear Hilbert form. You want to understand, and a fixed pairing between three Banach spaces, you want to understand when you have LP bounds. Okay, if the Banach spaces are LR spaces, interestingly enough, Benea and Muscalo obtain a very rich results, and probably the sharp ones, as it technically has not been proven that they are sharp, while we obtain absolutely no bounds. Okay, if we deal with the Banach spaces to be small LR spaces, well, they obtain everything. Well, we obtain something. In a regime in which the exponents LR are governed by this inequality instead of an equality. So this is a little bit unnatural because you would want to have an inequality here just by the Holder scaling. But since they're discrete spaces, you just have an embedding, and that can be used to gain something a little bit better. So now there's another So I will not go very much in the definition, but there's another special class of Banach spaces with a natural trilinear pairing that are Schatten classes. They're essentially spaces of linear operators or matrices with this, like with trace class operators. So a generalization of Hilbert-Schmidt, let's say, that are not Hilbert spaces. Bilinear Muscalo's technology cannot obtain any kind of bounds for these for such a Banach space, while in our result obtains essentially the same bounds that we get for small LR spaces. Okay. Now, okay, actually, before continuing, just one comment though. Interestingly enough, even though the results are different, both of them are sharp. Because what they do is they prove results in terms of the fact that all of the function space, like all of the Banach spaces are Lebesgue spaces with certain integrability exponents. We characterize the boundedness for general Banach spaces in which we ask some kind of interpolation property. So here we ask R intermediacy of Banach spaces, and that means that they are essentially interpolation spaces between Hilbert spaces and UMD spaces. So we characterize these kind of boundedness in terms of interpolation exponents. Now, the thing is, our result is also sharp because anything better than this, and in particular, anything that includes bounds for LR spaces, would prove an impossible result. That is, the bounds for BHT tensor BHT, because the second BHT is itself bounded on the product of LP spaces. So if you would be able to prove LP spaces without like just requiring boundedness of the trilinear pairing, you would manage to prove bounds for this thing that is known not to admit any bounds. So essentially, both of these results are sharp in the specific setting that they think about. So we think about interpolation scales, while they think about integrability exponents of pointwise defined functions. Okay. Okay, so let's see, how much time do I have?
1 second. You should have a good, maybe 10 minutes.
Okay. Yeah. Okay. I guess. So okay. So this is actually, before continuing. So this is kind of the overview of the results that are available, and I'd like to actually dedicate the rest of the talk on actually addressing some of the technicalities of how one deals and what are the difficulties of the bilinear Hilbert transform in the scalar case, and what are the modifications that are necessary to generalize it to the Banach value setting. So does anybody are there any questions so far on this kind of overview of the existing results?
So from what I read, I guess that you chose Schatten classes just for clarity, but any non-commutative LP will give you some results.
Oh, well, no. If they somehow they have to look like LR spaces in the sense that they have to embed into the higher exponent ones.
Okay.
So this is the thing that, like, since we're characterizing everything in terms of interpolation exponents, the thing is, like, we could do any non-commutative thing. The only thing that the property of the trace has to be that it is, well, is it atomic? No, I don't know if it's such a notion. So essentially, it's the same thing that this space is atomic, and there is a smallest measure that is 1. You have to have some kind of similar thing here, and to guarantee that embedding, because otherwise you can't, in this regime you can't even define a trilinear pairing between non-commutative LP spaces.
Okay. Thank you.
Okay. So as long as you have that, you can do absolutely anything. The thing is, well, Schatten classes are just a little bit more concrete. Okay. So let me actually then try to hand wave a little bit about the technicalities involved in the bilinear Hilbert transform. Okay. So let's get back to the picture of how the bilinear Hilbert transform looks like. So the bilinear Hilbert transform can be expressed, as we said, either in the Fourier side as a characteristic function of this slanted half plane, or in terms of its kernel representation. So the thing is, as usual, as done also in Cauldron-Sigmund theory, what we tend to do is we tend to somehow discretize or represent this kind of characteristic function as a sum of a bunch of different pieces. Now, the sum of the different pieces, though, has to somehow respect the symmetries of the operator. So, for example, when you do Cauldron-Sigmund theory, you decompose into pieces so that are translation, are invariant with respect to translation, and they are invariant with respect to scaling. As a matter of fact, that's essentially, if you wish, philosophically, the basis of the Wood-Paley theory. That's like that. That's what you do. So here we have the additional symmetry of modulation that corresponds to moving along in frequency space, so translation in frequency space along the singularity. So what we do is we first address the scaling. So we put little square blocks that we just consider the so here we have the function 1, here we have the function 0. So this is the multiplier. So here it is. Then what we do is we first start by putting just a sequence of rescaled blocks in which we put 1 on each one and 0 outside. So these are little tensor products of functions in frequency. Then once we did this, we want to make it uniform and move them around to cover all of the rest of the spaces. So what we do is we start moving them, translating them in frequency in like this. So we get this kind of decomposition. Of course, here it's very blocky. Then with some averaging procedures, you can actually get this specific characteristic function. So the thing is, now you can actually try to translate this kind of pictorial representation into a representation in a decomposition of the operator itself. So what does it mean to multiply a function in Fourier space? It means to convolve it in physical space. So what we do is we try to represent this little tensor product. So that is, well, how do we represent it? It has two parameters. One is a scaling parameter that determines how large it is, and there's a modulation parameter that determines how far, how long are we going along with the red axis direction. So here we encode these two symmetries with a dilation and modulation, and then here it is. Now, what we for S is appropriately chosen Schwarz functions. Now, what we do then is, well, we write down the frequency projection that corresponds in space to convolution. So here we go. And then what we do is, since we're averaging or summing over all of these pieces, we integrate in d eta and dt. And so we have the representation for the bilinear Hilbert transform that looks like this. Now, working with this directly is a little bit hard with the operator. So the standard thing that one does is dualizes with a third function and starts studying the trilinear form rather than the bilinear operator. So let's dualize with the third function. A little bit more of geometric construction and algebra allows you kind of to symmetrize this whole procedure and put a modulation and a dilation and a convolution on the third function too. Then what you notice is that the convolution is nothing else than just the integral pairing of a function with a translated, modulated, dilated wave packet. So here we obtain, after some manipulations, we manage to decompose the trilinear form associated with BHT as an expression that looks like this. Now, this expression is actually quite suggestive because up to some geometric parameters that have to be specified, the fact that here you have eta minus t minus 1 and so on and so forth, how does this thing look like? You see, it splits naturally into three pieces that are obtained, that are just the original function paired with a symmetrized wave packet. So you take some kind of test function phi, you act with the symmetries of your operator, you bring it to some other location and you test, so you pair. You do it for all three functions, you multiply them, and then you integrate over d eta dy dt, so like the parameter that governs modulations, translations, and dilations. So you integrate over the full space of symmetries of your operator. So essentially, you can represent, so here it is, this the whole operator in this way. So the form is just a product of these three capital F, G, and H functions that are coefficients defined on the symmetry space R3 plus of the problem, where the coefficients are obtained from the functions using this pairing. Okay, by the way, if you are dealing with Banach space valued functions, this representation should work exactly in the same way, except for here now your coefficients would not be valued in numbers. So these would be not numbers defined on the symmetry space, but they would be vectors, some Banach space, like Banach vectors on the functions valued in Banach vectors on the symmetry space. So now the thing is, the problem is that the additional degree of freedom of this, like moving in symmetry, actually complicates life a lot. So what one has to do is, well, one has to kind of deal with it by carving and decomposing this whole space of frequencies into smaller subsets. So let's actually consider what happens when we freeze the frequency. So we say instead of looking at the full frequency space with the whole invariance, we actually introduce a distinguished point, for example, the 0 point, that we can actually make it absolutely any other point, but what happens when we introduce a 0 point? So at this point, if we fix a point in frequency, the only wave packets, so only squares that are interesting to consider is the ones that somehow are related to this base frequency. So what do we mean by that? We only consider those squares such that either omega-1 or omega-2 contain 0. Well, or their sum. The sum appears because of the third function, the one with which you dualize. So one of these three conditions. Now, if you graphically, you can represent these portions of the squares that we introduced as being just something in a little cone that looks like this. Now, absolutely, like the whole idea of the proof is based on noticing the following thing, that only one of these three conditions can hold at a given time. And we can see that, for example, if omega, here it's omega-2 contains 0, so this is the case, all the squares have to be situated like this. So omega-1, first of all, don't intersect and also don't contain 0. So the other two regions would be this one and this one that correspond to omega-1 plus omega-2 containing 0, and this is omega-2. Okay. So once we look at this restricted version in which we restrict the integration of the parameters to only those parameters that create the squares associated to these three regions, this is what we get. Well, it's a specific case that I was looking at. The modulation disappears because essentially we up to a little bit of uncertainty we have fixed the modulation. So the modulation symmetry drops, and what you get is the following expression, in which you have the translation and dilations of wave packets. However, the wave packets now have a specific form. The second one, whose frequency interval contains 0, is just going to be any wave packet, while the other ones that don't contain 0 are what's called lacunary. So their average, so the integral of the wave packet, is 0, or that's the same thing as saying that the Fourier transform at 0 of the wave packet is 0, because 0 is not in the support of the Fourier transform of the wave packet, as can be seen from this picture. So now, if you look at this expression, if you translate it back, so here I'm just rewriting it into like the translations into convolutions, what you notice is that what you obtain is a form that very much looks like the trilinear form that is dual to a Coifman-Mayer multiplier. So once you fix the top frequency, you just collapse down to Cauldron Sigmund theory. Now, very simple way to kind of give you an idea of how to proceed with these bounds is, well, once you have this, what you do is you just use Cauchy-Schwarz, you square integrate and scale the two functions that have a psi, and you obtain Littlewood-Paley square functions, and you take the L infinity norm in the remaining one, you get a maximal function. And then, well, locally at least, you can imagine that this kind of thing is well behaved because square functions and maximal functions are bounded on LP. Okay, so that's the local and freeze frequency piece of it. And the rest, well, the rest is bookkeeping, because once you do one piece, you have to do like what remains, and then you have to do what remains, and so on and so forth. And you just have to be able to bookkeep and sum them up. And here comes in the other crucial ingredient, that is the outer Lebesgue theory. At this point, I think I'm running out of time, so I'll go quite quickly over this. The important thing is outer Lebesgue integration theory essentially introduces appropriate LP norms on the space of symmetries. Unfortunately, they cannot be classical LP norms on these coefficients because, well, because of the additional symmetry causes you like significant problems with measurability and things like that. So what you do is you develop this abstract integration theory that manages to bear in mind both how large these exponents are on these localized shapes that looks like these cones. These are called trees, and the size keeps track of how large the functions are, and then it keeps track of also how large these truncated cones are as you sum over them. So that is measured by the outer measure. And somehow the interplay between the two keeps track of gives you tools that keep track of like the bookkeeping of how you select and proceed. So generally the proof then falls apart into the following steps. First, you prove that this classical Lebesgue integral is dominated by an outer measure L1 type integral. So this outer Lebesgue L1 norm. Then you use an abstract result about Holder inequalities that that allows you to separate the three functions into other appropriate outer measure LP normed functions. And then finally, what you do is you actually show that these coefficients and these norms are bounded by the classical LP norms of the small functions that are used to define the capital functions. Okay, so that's how it, and this last step is called the embedding bounds. Okay, so, and if they involve some kind of selection algorithms or whatever that like have a flavor of like a Vitali covering lemmas and things like that, though they are a little bit different. Okay, anyway, at this point, I can actually just quickly write out what explicitly these objects are. Trees are, this is just a formal expression of the parameters that lie close to a certain frequency and lie around a certain point in space and below a certain scale. The size, so how large a function is on one of this set can be measured by saying, well, you take the L infinity, so something that looks like a maximal function around of these coefficients, so the L infinity of these coefficients that looks like a maximal function, and then you take an L2 norm in the regime when you're far, like in which your wave packets that define F have mean zero locally. So then this becomes a measure of how large a function is locally on a tree. The measure of how large a function is everywhere is just going to be the supremum of all possible trees. The measure of a tree is just going to be its top scale. And then, well, here are the objects, and then you introduce the integration theory. So if anything, the most crucial part of the integration theory is how do you define these LP norms? Well, you write down the super level set representation formally, but then you have to actually define what this object is, how the largeness of the function and measures of the set are defined. And here I just have a quick picture that relates it to classical Lebesgue measure. So you see the size, the problem or the advantage of this theory is that the size is not a pointwise value of a function, but it is a norm. So how can you say what's the measure of where the norm of a function is larger than lambda? It makes no sense. The norm is, it's not a set of points. The norm is one unique object that is defined on the whole function. So how do you define it? Well, you do the following. Imagine that you have this green function on R, so a classical function. You want to understand what is the super level set with respect to lambda. You fix lambda, you want to see what is the measure of the set where the function is larger than lambda. You can characterize it as being the measure of the smallest set that you have to throw away, the smallest set onto which complement you can restrict the function f and obtain a function that is in L infinity smaller than lambda. So this is actually the crucial change in the definition of the outer, like that allows the defining the outer measure Lebesgue spaces. Okay. So what are the novelties of the in the Banach space case? Well, first of all, locally on every tree, before we use square function, maximal function, in the Banach space valued case, we had to read with Alex essentially and familiarize ourselves with Banach space Cauldron Sigmund theory and re-implement all of like that, like, you know, the equivalent of Littlewood-Paley square function techniques and things like that in the Banach valued setting. So that was the first thing. That was elbow grease and essentially that. Then, well, let me skip the second point a moment. At the level of bookkeeping, we needed to introduce a good interpolation theory because, as you remember, our result is in terms of interpolation scale. So we needed to introduce a better interpolation theory that allowed both varying the exponents p and varying the Banach space in which the function was valued. That was actually like a particularly, well, that was like the main difficulty that required a lot of new ideas. And finally, there is one more issue that when you do the local Cauldron Sigmund theory, you have, you had Littlewood-Paley square function, and maximal function. And unfortunately, the maximal function in the Banach space setting, at least in that specific set, like in that specific format, does not have good properties. At least it is bounded by only for spaces like Banach spaces that have additional properties that we are not like we would want to avoid. Actually, our first draft and our first submission of our first paper, actually, we required that on that property on the Banach spaces, and the referee that suggested rejecting the paper said actually that property is too strong. You have to work to, like, you know, the good result would be without requiring that is expected to be true. And so what we did is we added a little bit of elbow grease more and actually went around the issue of maximal functions and managed to drop the hypothesis. The interesting thing about this technology is that actually it came from a completely different direction that is actually my main area of research, that is what's called uniform. Yes?
We need you to wrap up.
Okay. No, okay, yeah, that's it. Well, anyway, so it came from another area of research that is completely scalar valued, is studying how time frequency analysis, so this kind of the BHT that has this singularity degenerates if you start moving the singularity to just standard Cauldron-Sigmund theory. And that is not completely understood, and that's actually like the thing that I mainly specialize in. Okay. By the way, this is not the approach that the result that appeared in parallel to ours use. So Bilinear et al., they use other things that are time frequency projections that though do not seem to work well with the question of uniform bounds. So what are the future? Well, one thing that we're actively looking at is trying to prove BHT for Schatten classes in the or a semi-commutative BHT in which we have the equality rather than inequality, because somehow Schatten classes, in addition to like their interpolation property, have some specific, and the trace has some specific properties that make them a little bit more similar to function spaces rather than just abstract Banach spaces. So somehow maybe borrowing some ideas from the helicoidal method, we are, or maybe not, we are trying to actually show that for the specific examples of Banach spaces, we can do something better at using somehow some information on the structure. And very long-term project is actually trying to redo some of these questions about the bilinear Hilbert transform in a fully non-commutative setting. So already Cauldron Sigmund theory seems a very like almost beyond reach, because that's like actually there has been some progress, but it's like we surely do not understand everything yet. But at least I don't understand anything based on the things that I tried to read. So the question is, how do you even do BHT? How do you go beyond? Well, the hope for that is that at least we have a characterization of BHT, or at least a model for BHT that is expressed in terms of symmetries. So essentially what one can do is write down a fully non-commutative object that has formally the same symmetries, even and may, though that it doesn't really necessarily look the same, and then try to apply this, integration theory on the space of symmetries to maybe obtain some results. Okay, and I think that's it.
Thank you very much, Gennady, for the talk. Are there questions? I have one, at least one. So you're looking to adapt the helicoidal method to the semi-commutative version of the BHT.
Not really. No, we're looking to adapt our, like the outer measure approach to the semi-commutative BHT. And well, we actually, like, the thing is, like, there is some progress there that the specific form of the semi-commutative space allows for more interesting definitions. Than just generically the one that you could just write down with a general Banach space. So that, like, the thing, though it is true that if we get at any point we get particularly stuck, the failsafe, well, it's not a failsafe because it doesn't guarantee anything, but it would be always to go back and look at how the helicoidal method does it for commutative spaces, and maybe have some ideas from there. The thing is, like, that's actually kind of more or less left a little bit by itself. So we have some ideas, some drafts and things like that, but we haven't really developed it. The question is, but what if our spaces are actually commutative? So actual OP spaces, why does how do you use outer measure technology to reprove what the helicoidal method proves? And we didn't really have time to deal with it, but it's actually kind of a nice intermediate thing, just to compare these two results and try to transform one into the language of the other.
Okay, thank you. More questions?
So actually, there is a little comment. So in the semi-commutative case, though, the only thing that we can even make sense of as a question is for diagonal exponents.
Okay.
In the sense that it's not multiple vector values. So it's not LP like of R valued in a Schatten LQ class. It would be an LP of R valued in L Schatten P. So for now, like okay, technically for Schatten classes, we could write down the full like a mixed norm estimate, but like for more general semi-commutative things, I don't think it's completely straightforward in my understanding. Or
that's correct.
So even the diagonal case, that in the commutative case, so in the commutative case is just Holder's inequality. You just use fiber-wise plus Holder. In the semi-commutative case is completely open. Even the diagonal one. So that's actually like something to which we might be getting close right now.
All right. Then if there aren't more questions, then we thank you very much again, Gennady, for the nice talk. And we will even let you go have breakfast, I guess.
Thank you.